Hey, it's Dr. J. We're only going to do one lesson from one section from chapter 4, and it's going to be linear functions. So I'm going to kind of put everything related to linear functions in this one lecture, and then after this we'll move on to chapter 5. Okay. It turns out that most of what we're doing in this lesson was already covered back in chapter 2. The main difference is in chapter 2 we didn't have the concept of a function. We just referred to linear equations and slope and intercepts, and all the terminology is going to remain the same, but now we have an additional piece of information relating to a function. So without any further ado, let's just get right into it. Let's recall a linear equation. In two variables, can be written double T's there, as ax plus by equals c. This is called standard form. Okay, and we assume that b is not equal to 0. Now the reason why we do that is so that we can write it, because if b is equal to 0, then that means the y term would not be there, and it would not be a function. It would be a linear equation, just one variable. It would just be, ax equals c, and we're not going to be studying those in this section. Everything is going to be written as a linear function. So we can solve, or we can isolate the y, and this is called slope-intercept form. Intercept form. Y equals ax plus b. Now I will point something out. Capital A and lowercase a, capital A and capital B are not the same as lowercase a and lowercase b. I know, I had to do it, but it's just the way it is. Let me explain how that works. So we take something that's in standard form and we push everything onto the right-hand side, isolating the y. So we want to get the y all by itself. So what we're going to do is we're going to subtract ax from both sides. And I like to write it negative ax plus c. Okay. I don't want to write c minus ax, because my goal is to have the x as the leading the x as the leading term, and the leading coefficient would be a. Some books call this m, and I'll refer to that in a minute. So I'm going to divide everything by b. And we're going to write this as negative a over b x. I like to put the x off to the side. Plus c over b, and then we rename everything. This is the slope. That's a. And this is the y-intercept. That's b. So capital C over capital B, that comes out to be lowercase b. That's what we call the y-intercept. When you write it as a point, we write it as 0, comma b, like that, as a point. Or an ordered pair. And then negative a over b is the slope, sometimes called m. So if you've had an algebra class before, most common beginning, intermediate level algebra classes use the letter M. And then for really no apparent reason, we switch it to A. Mainly, I mean, I said there was no reason, but mainly it's because we like the alphabet, yeah? A, B. When we get to quadratic functions very soon in chapter 5, we'll have A, B, C, and A, B, C, D, and things like that. So we like to use the alphabet whenever possible. But, I mean, if you're still comfortable using M from your beginning algebra, that's certainly fine with me. I honestly don't care. As long as you know that it's slope. That's the most important thing. Okay, and then if the y is isolated, this is what we call a linear function. And we say y is a function of x. Or we sometimes say in terms of x. That means the same thing. Y is a function of x, or y is written in terms of x. Okay? And so what we often do is we omit the letter y, and we call it fx. And my friends, that is the only thing new in chapter 4.1, section 4.1, as it relates to chapter 2 and all of the linear graphs and linear word problems, you know they're coming, that we ended up doing back in chapter 2. All right, well, there you have it. I mean, I don't really have much else to say, except let's do some problems and see how this actually works in real life. Example 1. Solve for y in terms of x and express the result as a linear function. Oh, let me just say using, it's a better way to say it. Express using interval notation, using function notation. All right. I better give you an equation, huh? Negative 6x plus 9y equals 27. All right, so A, B, C, kind of like in the introduction. And now I want to solve for y, also known as isolating y. Sometimes you'll say solve, sometimes you say isolate. So we want to get the y by itself, so we're going to add 6x to both sides. That's because the 6x is already negative. Again, if the 6x were a positive, then I would subtract it. Just, you know, the opposite principle. Notice the way I write it. I don't write it as 27 plus 6x, because that's not the form we're going for. So we have a target in mind. We're going to write it as 6x plus 27. And then we're going to divide everybody by 9. 6 divided by 9, it's not divisible, but it is reducible. That's 2 times 3, and then 3 times 3. So we're going to reduce this to 2/3 as the slope. That's our A, that's our slope, or M if you prefer. And then 27 is divisible by 9. That'll be 3. And then we're going to express our answer using function notation. So we write y is f of x. Just keep that in your mind. And you just replace the letter y with f of x. Okay. Just for fun, let's graph this. Yeah, I know the question didn't say to graph it, but what the heck? I got some graphing time here. We'll just do it. So there's x, there's y, or you could call this f of x. Same thing. All right, your y-intercept is 0, 3. All right, so remember, this is the y-intercept. You can't just say 3, you got to say 0, 3. You can just memorize that. You probably already did in your last algebra class, but if not, you can kind of see why. If you plug in 0 for x, you get, I don't even have to do this, but I'm doing it anyway. If you plug in 0 for x, you get 2/3 times 0, that's gone, and then you get plus 3, so you end up with the point x equals 0 and y equals 3. And so I'm writing it as a 0.03. I don't ever have to say that again. I might as well get us off to a good start. Right? And then the slope is 2/3. I don't know if you can read that. Let me write it a little bit bigger. Slope. So we're going to go, starting here, we're going to go up 2. And we're going to go right 3. And that puts us right here. And there's our linear function. Okay, so this is the graph of the linear function f of x equals 2/3 x plus 3. I'm going to give you a couple free answers. The domain, -infinity to infinity. Yeah, that's a free answer all day long. Yeah, 100% free. The range is not free. You just look at the graph. Although it's kind of free, but you should still look to be sure. Look which direction the range is going. Range is the y values. So this arrow is going down forever and ever. That's -infinity. It's going down. That's the range. Range is the y values. And then look at this arrow. This arrow is going up forever and ever and ever. That's +infinity. So the range is cheap. It's not free. You should definitely look before you leap and make sure that you understand what the domain and range are. Okay. So there you have it. Linear functions, basically the same concept as a linear equation, just using the terminology from chapter 3 involving functions. Example 2. Solve for y. Express using function notation. Graph it, state the domain and range. All right, let's try another one. So what do we have? Negative 8x equals 32. Sorry, I meant 8y. Solve for y. So -8y equals 32. All right. Let me just make a mental note. If there is no x variable, then the slope is 0. So the slope is automatically 0. In other words, the line is horizontal. Yeah, I already know that before I even start the problem. Not a bad idea to kind of know what you're getting at here. So for this one, we only have one step. We're going to divide by -8. 32 divided by -8 is -4. Yeah. What this really means is 0x minus 4. That's what that means. You don't need to write that, though. You could just write -4. So you can think 0x minus 4, but what you're going to write is just -4. And then you're going to replace your y variable with f of x. This is what we call a constant function. It means that the output is constantly the same value. It's constantly equal to -4. That means my graph will be very, very easy. Constant functions are perhaps some of the easiest functions around. So when I draw my graph, I just go down to -4. Now the trick is you have to know what this means. This means the output is -4, not the input, the output. Output is the y value. Input is the x value. So make sure you go to the right -4. Sometimes I'll try to trick you by, I'm not trying to trick you, I'm trying to educate you, but in order to educate you, sometimes I'll put out some bait and see if you take the bait. Don't pick that -4, that's the input. We want this -4 down here. All right. Now, in order to make your graph stick on the computer, you have to click on any other point as long as its y value is -4. So you just pick any 2 points that have the same y value. I picked 0, -4, and it looks like 1, 2, 3, 4, and -4. It doesn't matter as long as you have 2 points that have the same y value. In this problem, the y value is always -4. Okay, so that's what a constant function looks like. So what's the domain? Well, I already told you it's a free answer. -infinity to infinity, that's free. Now, the range is not necessarily free. You got to look carefully. Look at the y values. Does it go up to infinity? Look at the y values of the graph. No, it does not go up. It stays flat horizontally. Does it go down to -infinity? No, again, it stays flat. It never goes down to -infinity. Yeah. If this were sound, it would go like this. It's just a constant note, whatever that note is, -4, if you want to call that a note. Yeah. It's a constant tone. It doesn't go boo, woo, woo. It doesn't go up or down or anything like that. It just stays flat. Woo! Like when you're dead. Yeah. That's another name for that is flatlining. Yeah. Everything is flat. Okay. So the range is just -4. We do not use parentheses. We do not use brackets. We use braces when the range only has one element. So use only when there is one element. Yeah, there's only one output, so we just use the fancy pants. All right. So there you have it. Example 3. Find the linear function that passes through the points -5, -4, and 10, 2. So let's start off with a graph. 1, 2, 3, 4, 5, 6, 7, 8. Good. Start off with a graph. So I've got -5, -4, -5, -4, right there. And 10, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 2. So there's the graph of the linear function. Now I have to find the function. This is just a picture of it, yeah? So if you want to be a real smart ass, you can go, I found it. There it is. Yeah. You told me to find it. I found it. There it is. Yeah. Yeah. Well, that means you graphed the linear function. You haven't really found it yet. You haven't found it until you give me an equation that tells me what it is. That's what it means to find something. This just means you've seen it. I've seen the linear function, but I haven't really found it yet. I know. Like, I have to be that way. I'm sorry. Okay. And so now we need to find out what the slope is. All right. There are several ways to do the slope. One way was way back in chapter 2. I just taught you the formula. x1, y1, x2, y2. And you could just use the formula y2 minus y1 over x2 minus x1. So 2 minus -4 over 10 minus -5. So the slope is 6/15. You have to simplify that. 6 is 2 times 3. 15 is 5 times 3. So I reduce it by a factor of 3. So those 3's divide out and you get 2/5. So that's the slope. Yeah. There is an easier way, actually. You can actually just count. 1, 2, 3, 4, 5, 6. Up 6. Yeah. And keep track of how far you went. And now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the slope is 6/15, which is still 2/5. Yeah. So I really want you to know both ways. I want you to know how to count the slope. I also want you to know how to calculate the slope. And if you really want to be safe, do both. And I've been doing this for 30 some odd years. And, you know, if I make a mistake counting, well, then my equation will catch the mistake. And you know me, I make a lot of mistakes. If I make a mistake calculating with the formula, then the picture or the counting method will sometimes ensure my result is appropriate. Okay. So that's the slope. The next thing we need to do is find the y-intercept. Sometimes you get lucky and you can see it. Yeah, the y-intercept is -2. That's my guess. Yeah, I wouldn't trust my guess. Yeah, I think it's going to be negative 2, but it could be negative 2.5 or negative 1.9 or something like that. It could be something close to negative 2, and the graph pictures, images sometimes lie. They don't really tell you the truth. So why don't you just go ahead and guess based on the graph? We think it's negative 2, so that's our guess. I'll just go ahead and write negative 2 right there as a guess. But I want to make sure that it's actually negative 2. So this is the way you do it. All right, to verify the y-intercept, write y equals ax plus b, and plug in a for slope. Okay. And just verify that if I plug in one of the given points, plug in 10 for x, and plug in 2 for y, I'm just verifying that b comes out to be negative 2. Yeah, that's b. Y-intercept b. I know my writing is getting really sloppy. There's negative 2. That's what I think it is. All right, let's see if that's true. I need to erase this. Let's just write up here. Slope is 2/5. Don't forget that. All right, so what do we got? We got 2 equals 2/5 times 10 plus b. Remember, 10 is actually 10 over 1. Keep that in mind. So that's going to be 20/5 plus b. Yeah, 2 times 10 is 20. You're going to reduce that. It's going to be 4 plus b. Subtract 4. And we get negative 2 as expected. Okay. So, again, if you are 100% confident that that was negative 2, if there's no doubt in your mind that it's negative 2, then the verification is really just for peace of mind. But if you already knew it was negative 2, then you're already done with this problem. Okay. Let me show you how to package up the results. Oh, I should mention that I used 10 and 2. I could have used these 2 points, but I had them covered up with my board, so I didn't use them. But just in the same way, you could have used these 2 points, or this pair of coordinates, and plugged them in there. All right, so here we go. Here are your answers. Your slope, 2/5. Your y-intercept, be careful. You want to write it as a pair. 0, negative 2. And the linear function, f of x equals 2/5 x minus 2. Make sure that the x is either in the numerator, like that, or I prefer it off to the side, but do not put the x in the bottom. I will mark it wrong. So if you accidentally put the x down in the bottom with the 5, I will have to mark it wrong. It's not that I want to. I really don't want to. So that's why I'm telling you, don't put it in the bottom. Don't put it in the denominator. It turns out, we'll find out in chapter 5, but if you put an x in the denominator, it ends up curving the line. It's no longer linear. It becomes reciprocal, which is one of the functions we learned about in chapter 3. But again, every graph in chapter 4 or in this lesson should be a line, should be a straight line. Same question, find the linear function. passing through -5, 3, and 6, 3. All right, -5, 3. So 1, 2, 3, 4, 5. 1, 2, 3. Right about there. Yeah, -5 and 3. 6, 3. 1, 2, 3, 4, 5, 6. And 3 again. Oh no, look. It's horizontal. Yeah, both points have the same Y value. It's called the same output. Yeah, that's the Y value. We're done. This is a free answer. Yeah, the slope is 0. Yeah, you don't have to calculate anything. Don't even waste your time. Don't even bother counting. Don't bother using a formula. Use your mind. It's horizontal. Horizontal. The slope is 0. Okay. The Y-intercept, 0, 3, right here. Yeah, don't just say 3. Okay, I know that'll happen on the quiz or the test because you're going to go, oh, 3, yeah? Everybody knows it's 3, right? But it's 0, 3. Has to be in the right order as well. Okay, and then the linear function, f of x is 3. The function is always equal to 3. That's essentially what that means. Okay. So that's one type of free answer, horizontal. I'll give you another free answer. If I give you the slope and the y-intercept, the answer is free. The slope is A, the y-intercept is B, and we're talking about functions. So there's another type of free answer. Find the linear function with slope -6, passing through 0, 4. All right. The slope is your A, and if the x-coordinate is 0, then this y-coordinate is B. All right. I know my B's sometimes look like 6s, but I have to be very careful. That's a B. So this is B. So free answer, f of x equals -6x plus 4. Not too bad, huh? If you knew all this material back in chapter 2, then you're going to breeze through this one section of chapter 4. You might be wondering what you're missing in the other 2 sections. You might not wonder. It's just more word problems. So what I decided to do was just put the word problems that I want you to know for this course, and I put them all into 4.1, and then that enabled us to skip the rest of chapter 4. If you are reading the book or following along with the book, there's a couple extra sections in chapter 4 that I will not be assigning anything, or I won't even be testing you on them. I'll put everything into section 4.1. Okay? Let's do another one. Find the linear function with a slope of, I don't know, 2/3 passing through the point. 6 and -8. So notice that this is not 0. So this is not the Y-intercept. Yeah. So it's not free. You have to pay. Bummer, huh? I'm not going to give you every answer for free, but I will give you several. Yeah, every time there's something that's free, I will be the first one to notify you that it's free. I've been doing this for a long time, and I kind of keep a running record of how often my students take the free answers. And it turns out it's only about 50% of the time. Yeah, you would think that if I give free answers, everybody would take it, or maybe 90%. Almost everybody would take it, but it's only about half of my students actually take the free answer. So I hope that you are one of the half of the students that'll actually take the free answer. So for this problem, we're going to use what's called the point slope formula. Remember this from chapter 2, y minus y1 equals a x minus x1. And again, some folks use m instead of a. So the slope is a, previously known as m. The point is x1 and y1. So 6 is going to go here, and -8 is going to go way over here on this side. Okay, so I got y minus -8. Be very careful. I know I've mentioned this before. Don't just write y minus 8. It's y minus -8. And then you have a is 2/3, and then x minus 6. Yeah. Again, the 6 is a positive, but when you plug it into the formula, it becomes -6. So be careful with negative signs. Distribute to get rid of all your parentheses. I did that with mental math. Maybe you want me to talk through that. 2 times 6 is 12. 12 divided by 3 is 4. Yeah. Or there's another way to do it. 3 goes into 6 2 times. 2 times 2 is still 4. And then the third way to do it is to do it on your calculator and hope you get 4 and you don't get a decimal. If you get a decimal, you probably did something wrong. And then -8 from both sides. So you're going to get 2/3 x minus 12. And so the linear function, the slope is 2/3. I don't know if you can see that, 2/3, and the y-intercept is 0 and -12. Okay, that's it for the abstract problems, just abstract algebra, just solving and answering the questions in terms of slopes and intercepts and maybe some graphing and such. So these 6 examples should get you through about, I don't know, half the homework. The second half of the homework is all about word problems. So now we're going to start doing some word problems. Most of these word problems we've already done. And I did get a lot of feedback, emails, Zoom, face-to-face comments where people were telling me they hate word problems, or they suck at word problems, or damn the word problems, or whatever it happens to be. And I understand that feeling, I understand that sentiment, but I'm going to do them again. Okay, so that's the best I can do. Is I can say, well, I can't get rid of word problems any more than I can, get rid of, any of the other problems that we have in the real world. I mean, the world is full of problems, right? And we have to sort of solve them. Here's what I will do. All right, what I will do is I will try to motivate the word problems with some reality in there, and I will also give you some advice. Everything you need to know about word problems, you already know. You've already seen it in chapter 2, essentially. There might be some new terminology, there might be some new vocabulary words, but there really are no new skills. I'm not going to teach you how to solve for something that you don't already know how to solve for. So remember that. I will never give you a word problem that you can't handle. All right? It'll always be something that you have seen before. Okay, and that's the best I can do for word problems. So next, we talk about applications of linear functions, also known as word problems. One of the things that I will point out is that we've kind of already discussed this in the past, temperature. Temperature scales. There are 2 different temperature scales. There's C, which is called Celsius, also called centigrade. Centi means 100, grade means mark. So centigrade means 100 marks. Yeah, so that's the reason why Celsius looks like that. And then there is Fahrenheit. I always spell it wrong. Fahrenheit. Fahrenheit. There it is. Fahrenheit. Fahrenheit doesn't have another name. It's just called Fahrenheit, yeah. You might just know it as normal. If you live in the United States, it's just the normal way that we measure temperature. It turns out the rest of the world is using Celsius and we use Fahrenheit. We're kind of slow here in the United States. We're slow to catch on to change. When things are changing around the rest of the world, we in the United States don't want to change. We want to just stay the old, comfortable way, okay? And then you might also recall that water is a very important molecule. I was about to call it an element, but it's not. It's a molecule. Water is an important molecule on Earth. Of course, we all can't live without it, but there's 2 things that you should all know by heart. Water boils at 0 degrees Celsius, which is equal to 32 degrees Fahrenheit. And water, sorry, why did I say boil? freezes. As soon as I wrote it, I went, wait a minute, boils? It freezes at 0 degrees Celsius. It boils at 100 degrees Celsius, or 212 degrees Fahrenheit. Okay. Boiling is essentially hotter, obviously hotter than freezing. And this is reason why it's called centigrade. There's 100 marks, yeah? Centigrade, 100 marks between 0 and 100. So between boiling and freezing, there are 100 marks. Notice Fahrenheit does not have that. Fahrenheit has much more than 100 marks. It actually has 180 marks. Which again, 180, if you think about it geometrically, 180 means to turn around, right? If you turn something around 180 degrees, that's the opposite. And so people think of the opposite of boiling as freezing. So that's why those are kind of like opposites. They're 180 degrees apart. It's again one of the reasons why we use the symbol degrees. That's the symbol for degrees, a circle. Okay, again, these are things that you should already know. By heart. Right? If you are an adult human that lives on Earth, you know these things, right? And if you don't know them, it's pretty easy to remember them, right? So now's your time, okay? Anybody that's ever done any cooking knows this, and if you take a chemistry class or something like that. So I know I've already taught this to you guys before, but I had a lot of people being confused by this, so I'm giving it another approach. And so what we're going to do is we're going to let Celsius be X. Okay. And then we're going to let Fahrenheit be F of X. F of X. So we're going to write example 7. We're going to find a linear function, f of x, that gives us the Fahrenheit, that gives us the Fahrenheit temperature in terms of the Celsius temp x. All right, now obviously my board is not going to be big enough to fit these giant numbers here, so what we're going to do is just change the scale a little bit. So x is going to be Celsius. F of x is going to be Fahrenheit. All right, so in other words, we're going to input a Celsius and output a Fahrenheit. Now we already have these ones that we've memorized, yeah? Now I don't know, I have a very diverse group of students. Some of you have been to Mexico or Canada or Europe or anywhere around the world, and you already know Celsius pretty good. I have to admit that I actually don't. Honestly, I only memorize a couple, maybe 2 or 3 different temperatures in Celsius. And Fahrenheit I know pretty well, but Celsius I still have to figure it out when the time comes. So 0 degrees Celsius means that you are here, 0. That's x. And then f of x is 32. Now I'm just going to make a mark and call that 32. I'm obviously not going to count 32 steps on this graph board. All right, I don't have a big enough graph board. All right. And then the same thing here for Celsius. I'm going to go 100. All right. And again, I just want to make it look like 100. I'm not really counting to 100, so again, not to scale. right? I'm not actually counting to 100. And then 212, I'm just going to make a mark and call that 212. All right, so I've got 2 points. All right, and we're going to find the linear function based on these 2 points. Since I have them on the graph, I can go ahead and erase these ones. First, we want to find the slope. All right. So we can do it by counting, or we can do it by the formula. All right, let's use the formula. y2 minus y1. Remember, y means the same thing as f, output. I'm using f for function. I'm also using it for Fahrenheit, actually. Okay, and then I got x1 and x2. So 100 minus 0. So the slope is 9/5. Again, I'm using A for slope. You could use M if you still like that. 180 divided by 100 is 18 divided by 10, 18 tenths, which is 9/5. Or if you prefer decimals, in this case, I would also accept 1.8. Means the same thing as 18 tenths. Yeah, you can just jump right to here. 18 tenths is 1.8. Okay. And then the B is free. Just look. Come over here and look. That's your freebie. Aren't you happy when that happens? I call that a freebie. Yeah, you got a freebie. 0, 32. That's a free B. So B is just 32. All right. Find a linear function. So our answer, f of x equals A. A is 9/5. X plus 32. All right. I would also accept 1.8x plus 32. Your choice. And there you go. So what is this function good for? You know, what is it good for? I used to get this question a lot many years ago. I don't know if, times are changing, students are changing, I'm not sure. But I would say, back in the 90s when I started teaching, mid-90s, 96, 97, all the way till around 2001, 2002, in that period of my teaching profession, I would often get this question from the students. What is this good for? What am I going to use this for? How am I going to ever use this in my life? And I would often try to come up with examples on how students could use math in their everyday life. Now, lately, what I've gotten is just, I don't care. Most students just say, I'm never going to use it. I don't really care. Just please tell me the question has changed to, Dr. Jordan, tell me what I can do to pass this class so that I never have to do this ever again in my life. So whether you're on that side or this side of the issue, I'm still going to tell you what it's good for. What can you get this for? Suppose you're in Mexico. Yeah, and it says on the TV, it's going to be 35 degrees today. Yeah. And by the way, when you're watching the television in Mexico or in Canada or anywhere in South America or anywhere in Europe, they're not going to say Celsius and Fahrenheit, and they're not going to give you a whole lesson on Celsius and Fahrenheit. They're going to do the same thing that our news does here in the United States. They're just going to tell you the temperature. right? So you're in Mexico and the television says it's going to be 35 degrees today. What does that mean? Yeah, what does that mean? I don't know. What does 35 degrees mean? How hot is that? You know, I live in the desert. I've been here most of my life. Yeah. So what is 35 degrees? Is that 80? Is it 100? Is it, 50? What is it? Is it 75? What? It's certainly not, 35. 35 here in the desert would be free. I mean, it'd be not literally, but it would be pretty damn cold, right? 35 degrees. So what you do is this is X. Celsius is X. Yeah. So you're going to plug this sucker into this function. Replace your X with 35. I'm using this version, the 9/5. If you prefer, you can use the 1.8. It will be the same thing. Okay. 5 goes into 35 7 times. 9 times 7 is 63. You don't do anything on the left-hand side. This just reminds you of what you started with. You started with 35. And then you plug it in. It goes through the function. 63 plus 32 is 95 degrees Fahrenheit. So it's nice day. At least in my world. 95 degrees is a very nice day. All right. It's a little toasty, but it's nothing to cry about. You certainly don't need to go inside. You could go outside at 95 degrees. Okay. So that's what this is good for. All right. You plug in various temperatures for Celsius, and it will tell you what the corresponding Fahrenheit temperature is. Suppose you want to go the other way. Find F inverse of X. Yeah. So find the inverse function and describe its purpose. No apostrophe on its. Describe the purpose. In other words, what is the inverse used for? What is it going to do? Okay. Let's go ahead and do it. Yeah, find the inverse function. So this will be a little review of 3.7. 3.7 review. You first write y equals. Remember the steps? First write it as y, then switch the x's and y's. All right. I like to take it one step further. I like to actually write the y on the left and write the x on the right. So I not only switch the letters, but I also switch what side they're on. I like to put this 9/5 over on that side and then put this x on that side. You'll see why in a minute. I'm going to subtract 32. So now I have 9/5 y equals x minus 32. Then I'm going to multiply both sides by 5. So now I have 9y equals 5 times x minus 32. I'm not going to distribute quite yet. Maybe I'll distribute later. And then I'm going to divide both sides by 9. And this is one of the cases where we typically do not distribute unless you really want to. And then we get rid of the y and we call this f inverse of x. The reason why we typically leave this one in parentheses is because it's not divisible. 32 is not divisible by 9. And so if you distribute the 5/9, it's not wrong. I would still mark it right. It's just not going to be, it's not going to be very simple. It's going to look a little bit more complicated, so it's better to leave it that way. All right. Another reason why I try to avoid the decimals, although they are legal, is 5/9 is 0.55555555555555555. Right? If you ever done that on the calculator, you ever play around with the calculator when you were a kid? Yeah, look what happens. That's 5/9. It's not nice, right? It's an infinite repeating decimal. It's much easier just to write 5/9 than it is to write 0.5555555555555. So decimals are okay sometimes. They work pretty good when money. In a minute, I'm going to do some money problems, and you'll see what that's good for. Okay, so there's your inverse function. What's the purpose? So f inverse of x is 5/9 x minus 32. If x is Fahrenheit now, I spelled it wrong again, Fahrenheit. Fahrenheit. If x is Fahrenheit, then f inverse of x converts it into Celsius. All right. Abstractly, you can think of it like this. Here's C, here's F, here's degrees, degrees, and then you have the mother function, F. Notice it's not the same F. Capital F means Fahrenheit. Lowercase f is the function. All right. So the original function converts from Celsius to Fahrenheit. The inverse function converts from Fahrenheit back to Celsius. All right, so for example, if x is 68 degrees Fahrenheit now, then f inverse of 68 would be 5/9 times 68 minus 32. 68 minus 32 is 36. I just did that with my head. I hope it's right. I know I'll get some emails if it's not. 9 goes into 36 4 times. So that'll be 20 degrees Celsius. Yeah. Which, if you live here in the desert or you grew up here in the desert, you know that 68 degrees is kind of cold. Yeah, kind of cold for the desert. Yeah. But we would say 20 degrees Celsius. So it sounds a lot colder, doesn't it? Especially if you grew up here. 20 degrees sounds cold, but 20 degrees is 68 degrees Fahrenheit. All right, so that's kind of an introduction to word problems. So what I'll do is I'll do a couple more. Most of the word problems, in fact, I think all of them today in this part of the lesson are going to be review problems from Chapter 2. I will post a Part 2 video that's just new word problems that we might not have had or we might not have covered in Chapter 2. So I think I have time for 2 more. And these are review problems from Chapter 2, as I mentioned. Example 9, depreciation. Suppose a company purchases a new computer. So we've done this before. I think we did it with a truck or a bulldozer or a car or something like that. And today I'm calling it a computer. But depreciation essentially is what companies use to depreciate the value of an object. They can write it off on their taxes. They can also replace that item when its useful life is gone. So a new computer for $2,850. They consider the useful life to be 10 years, after which the value of the computer is only how much is the computer going to be worth? It's only going to be worth $500. Right. And I know that's not zero, but we still call it useful life when the value gets so low, close to zero. And in this case, 500 is close enough to zero. We sometimes refer to that as the salvage value or the resale value or the Craigslist value if you wanted to sell it on the internet or something like that. In a car, they call it the Blue Book value or something like that. Okay. So find a linear function that gives the value as a function of its age, t. V stands for value, T stands for time, which is another way of saying how old it is. So here's the idea. The value is going to act like Y, and the age is going to act like X. And the reason why I want you to know that is because I don't want you to think that every time there's a new word problem, you need a new system in order to solve it. You don't. The same system that we've always had, X and Y, okay? And if you ever get confused, X is always going to be time, all right? So whatever is not time, that's automatically your Y. So don't memorize who Y is, memorize who X is. X is usually time. Unless I tell you otherwise, X will be time. Of course, there will be some problems where X is not time, but it's the same idea. All right? So we call this depreciation. You could draw a graph if you wanted to. I'm not going to. I'm just going to go ahead and do it. All right? So I've got my V1. Yeah, I've got my V2. Yeah. And then I've got my delta t here. Delta t is also called the change in time. Yeah, the change in time is called delta t. That's 10 years. Notice they didn't give me, this problem didn't give me T1 and T2. I don't have the two. It doesn't even say what year this is. I don't have any idea what year this is, right? This is just t changing in time. Okay. So we want V of t to be AT plus B. That's our goal. All right. So you want to keep your eye on the goal. What do you want? All right. So I got to erase some of this stuff. All right, so let's find A first, slope. That's the A. Yeah. That's going to be delta V over delta T. Yeah. Delta V is the change in value. V2 minus V1 over 10. Because I already know that delta T was given to be 10. So V2 is $500 minus V1 is $28.50 divided by 10. There's no shame in using your calculator when the numbers get into the hundreds and the thousands. I'm going to do it. $28.50 500 minus 2850 is negative 2350 divided by 10 is negative 235. Okay. And then B is free. B is also the value of the computer when you first bought it. All right. So let's make a note here. Note, in depreciation problems, the purchase price is V1, and it's also the Y-intercept, B. Yeah. So we're basically done. V of t is negative 235t plus the Y-intercept, which is the purchase price, 2850. All right. And again, I didn't draw the graph. I said I could have, but I mean, I'm already on over an hour now. If you drew the graph, this 2850 would be where it crosses the y-axis when you draw it. Okay. So that is depreciation. Let me just, before I continue on, let me just explain what this means. Depreciation is negative, and it means it's losing value of $235 at a rate, losing value at a rate of $235 per year. That's what A means. It's the rate at which it's depreciating. So every year your computer, this computer, is worth $235 less than it was the year before. And then the 2850 is just the purchase price. Also called the initial value. Now, if you take other classes, this will contradict a little bit. Some other courses call the initial value V0. They put a sub-zero there. I've already used V1, and I'm not going to change what it's called now. So you really don't have to even use a symbol. You could just say the purchase price, V, value, what was originally purchase price. Okay. Suppose you purchased a computer and you want to know how much it's worth. Just a side question, how much is this computer worth 3 years after its purchase? Well, there's a couple ways to do it. Some folks just do this with mental math, right? They purchased it at $28.50. It's losing value $235 a year. So using mental math, just subtract 235 3 times, and that should tell you the new value. But why go through all that trouble if you have a function that does it? Just plug in 3, and you don't even have to use mental math. You can just use the function to do it for you. As soon as you use the function, you kind of see what the function's doing, right? It's taking the rate of depreciation, it's multiplying it by 3, and then it's subtracting it from the purchase price. Again, I'm using calculators when the numbers get into the thousands or the hundreds. 235 times 3, so that's negative 705. And then you're going to negative 705 and 2850, and you're going to get $21.45. Dollars, of course. So that's how much the computer would be worth 3 years after you bought it. Okay, got time for one more. Depreciation always has a negative slope. I make sure that I use the word depreciate so that you know that you better get a negative slope. If I give you a problem and I use the word depreciate and you do a calculation and this accidentally comes out positive, that's a red flag. Immediately you made some mistake. Okay. The opposite of depreciation is appreciation, also known as population growth. I mean, I guess if it's money, you would call it appreciation of value. The value is going up, like a house, right? Typically, cars and computers and other types of consumer items go down over time, but investments, at least ideally, investments we hope go up, although that doesn't always happen. Remember, mathematics is an idealized subject, so all of these problems are like as if we lived in a perfect world of pure ideals, mathematical principles, and you don't have the ugly, dirty reality of the real world, which is kind of neat, right? You can solve a problem without all the politics of what's going on in the real world. So population growth. One thing that is true, at least most of the time, is that the size of your town, the size of your state, the size of your country is going up. Of course, there are some examples that go the other way, especially when you're talking about nature and wildlife and things like that. But I'm going to go ahead and do a growth problem here. Suppose in 1983, the population of a small town was 400 people. Okay, by the year 2008, the population had grown or increased. All kinds of clues, little clues that I'll put in the word problems to tell you whether it's going up or whether it's going down. So I'll say increased, to 7,900 people. All right. Find a linear model. By the way, model is the same as function. You know how I love to teach you guys lots of new words. If I say find a model, I really mean find a function. Same thing. A model is a synonym for function. So find a linear model that gives the population. Why don't we use the letter P as a function of T, the number of years since 1983. Basically, this is the same problem that we just did. The only difference is this is growing, and so growth means that the slope will be greater than 0. Yeah, the slope will be positive. So if you make a calculation error and you end up with a negative slope, you did something wrong. All right. So we've got T1 is 1983. T2 is 2008. P1 is 400 people. P2 is 7,900 people. All right. Now this is taking up all my room here. So find a linear model that gives the population as a function of t. So I'm just going to erase this and write our goal. P of t is AT plus B. A is the growth rate, also known as the slope. We call this the annual growth rate per year. And then B is the initial population in 1983. All right, so in other words, we're treating 1983 as if that was the first day of the world. Yeah, because we don't have any data that goes back farther than 1983. So it's as if everything started at 1983. All right, so if we were drawing a graph, 1983 would be the y-axis. That would be 0. Okay, and we're not going back into the negatives. So we'll never even know the 70s existed. All right, you might as well take your free answer. Initial population in 1983 was 400. So that's a freebie. Yeah. Initial population, 1983. That's free. 400. So I already know that's going to be 400. So the only thing we have to do is find A. All right. A is delta P over delta T. Yeah. P2 minus P1 over T2 minus T1. All right. So P2, 7,900 minus P1, 400 over T2, 2008 minus 1983. Again, there's no shame in using a calculator at all. I think you don't need them here. That would be 7,500. Let's go ahead and do that one on a calculator. 2008 minus 1983, 25 years. Oh, I should have known that, right? I didn't really need it. Sometimes when you use the calculator, as soon as you do it, you go, oh, I didn't really need to do that, did I? But you know what? I'd rather use the calculator and be right than have you guys sending me emails telling me that I made a mistake. Okay, and so now I've got 7,500 divided by 25 gives me 300. All right. So this is the slope. It's not the answer. I really shouldn't be boxing it yet. All right, and then this is the y-intercept. Although it's not really the y-intercept, it's technically what we call the p-intercept, right? Because p is acting like y, yeah, and t is acting like x. So our growth model, and the same thing works for animals, you know, dogs, cats, sheep, bison, whatever, humans, rabbits, whatever. So your growth model is P of T is 300 people per year. So put the variable next to the slope. That tells you how many people per year are moving into this town, plus the initial population in 1983. Okay. Now we don't know when this town first started. Obviously, every town starts with nobody. Somebody lived there, but we're assuming that this town started in 1983 with 400 people. Okay. So there you go. There's a population growth model. What is it good for? It's good for the same thing that all the models are for. It's good for making predictions. Okay. So what is the population in 2020? Now be careful. Don't plug in t equals 2020. Don't do that. Instead, t is the number of years since 1983 So you have to first subtract 1983, 37. I bet you I have a student. I bet you I have at least one student that was born in 1983. Yeah. If you're out there, I know that you are going to be 37 this year. Or maybe you already turned 37. Yeah. So this is going to be your T, and now you're going to plug it in. If you plug in 2020 into this, it's going to blow it up. It's going to be like billions of people. It's not going to make any sense. All right, so the population is growing by 300 people per year for 37 years. So I multiplied. That gives me 11,100 plus the original 400 people that live there. So this is the population in 2020. You don't even need the comma. In fact, it's probably better if you don't put the comma. So it's 11,500 people in the year 2020. All right, maybe they have a stoplight now. Yeah, maybe. You get 11,000 people, you're probably going to need a Walmart and a stoplight. Okay. So I know you've seen this problem before. I think we did it with sheep or coyotes, or I don't remember what it was. It was something like that, right? Buffalo or something like that. The whole idea is now we're calling this a function. That's the only difference. And until next time, part 2, this is Dr. Jordan. I will see you on the internet.